Okay, so you guys learned about the miracle that is the fundamental theorem of calculus, I take it, yeah? And do you guys find it miraculous? I can just feel the excitement coming out of the crowd today. So let's just recap before beginning. Can anyone state for me the fundamental theorem of calculus part 1?
If f of x is continuous and differentiable, then the derivative of big f of x is equal to the derivative of big.
Sure, yeah, it's something along the lines, if we make f of x this function, which goes from an arbitrary point on the real axis to x of this little f of t dt, then the derivative of this function is actually equal to f of x. Okay, so this sort of codifies the relationship between the antiderivative and the integral. What about fundamental theorem of calculus part 2? What does that one say? Yeah, good enough. Okay, so if we have f prime is equal to f, that is if big F is the true antiderivative of little f, then we have that the integral from a to b of f of x dx is equal to f of b minus f of a. And which is an amazing, amazing thing, that we have this very speedy way of computing the area under a curve by finding one antiderivative rather than going through all of the rigmarole of doing the geometric Riemann sum and then finding that limit. This is way faster. You guys familiar with this notation? Yes? Yep. So suffice it to say that if I write this, this is a notation for saying substitute b into f and subtract substituting a into f, right? So just basically this is notation for precisely what I've written here.
So this be considered the proof?
No, the proof should have been the whole class that you did last time. Right? It takes a while to do the proof. Don't you remember you set up, you did this, and you should have used the limit definition of the derivative to find what the derivative of this is. Really? Oh. Oh, only, so he didn't build it for you. Well, can't do it again, right? So we got to keep moving. Did you guys learn about negative area? Oh. Okay. So we're finding area under the curve, right, using a Riemann sum. And we've been very careful to give you examples which are like positive, usually. What you may not have realized is that if you do the Riemann sum over this, what do you get? Something greater than 0 or less than 0? Why?
Because the point to the right will be smaller than the one to the left.
Well, it's because we're forming a height. Remember, we're using the function itself to form heights? So if I use this evaluation, if I evaluate at that sample point, f at that sample is going to be negative, right? So I have a positive width multiplied by a negative height, which is going to give you a negative area, right? So area under the curve, this is called signed area, right? So whenever we draw pictures like this, it's presumed that A and B represent positive quantities, right? I'm saying there's a positive amount of area in here, a positive amount of area in here. But if this is a function f from 0 to 1, then we'd say that the integral from 0 to 1 of f dx is a minus b. Right? You guys get that? So what's the integral of sine from 0 to 2 pi?
0 minus 2 pi, basically. The area from 0 to 2.
What's the area over this? What's the area? 0, right? Because these areas are equal, right? So if you take the integral over, it's possible to get a 0 integral, right? Even though you have non-zero areas in your integral. Okay, what else did you learn?
So it's possible to get a negative area answer.
Yeah. In that case, right? So area underneath the x-axis is negative area. More generally, area that are formed with Riemann sums taking samples in the negative region, right? Because you can also do integrals along y. Right, so if you're in the negative region of y, then you'll get negative area, right? Because you can get negative height because of the nature of the sampling. Okay, so did you learn an integration technique on Monday?
Is it where we plug in the d value into the antiderivative? Subtract
Yeah, but generally it was called substitution. Right, so you also learned a technique called substitution, which is basically reverse chain rule, right? Is that how it was presented to you? No? See, this is why I don't like missing lectures. Okay, so what is the chain rule? If I take f of g of x and I take the derivative of this, you get something like g prime of x out. You really didn't learn substitution the other day?
We did.
Oh.
And then you plug in
Reverse product rule. Okay, whatever. So this is going to be equal to the integral of f u du when u is g of x. It's not too important you understand like the generic statement. The technique is a lot more important. So let's just jump to an example. Would you be able to do this guy? 2x plus 1. Is this in your wheelhouse? Okay, so let's try to integrate this using a substitution. What substitution seems well useful here? Yeah, so usually these square roots or anything within a set of brackets to some sort of rational exponent. This is a good candidate for the substitution. Remember, this may fail. Right? You may have to try several different substitutions before you find one that works. Right? So don't get frustrated if you do something and it doesn't work. Right? Like, throw away the piece of paper and try something different. So, all right. So we're going to say u is 2x plus 1. That means if I take the derivative, you're going to get 2 dx plus 0. Is everyone comfortable? Did everyone see how I got this? If you want, you can say du over dx, but it's a lot more cleanly just to do it on one line. Okay, so we have du is equal to 2 dx, which means dx is half du. So we get this substitution, half du. Okay, now what? We can't do anything with that. We have an x now. How do we get rid of the x?
Well, we can isolate the x in terms of u.
Yeah, so we do know the relationship between x and u. So if I rearrange this, you're going to get what? U minus 1 half is x. Let's just make sure that that's what I got here. Yes. Okay, so what does that mean I can write this as? Well, this is going to be integral, so u minus 1 half root u 1 half du. Let me just grab that. This is going to be equal to what? 1/4 integral u minus 1 root u du. Can you do that? Yes, miss.
Wouldn't you just fold it, factor it?
Distribute.
Distribute.
The opposite of factor. Yeah. Okay, so you got 1/4 integral. That worried me. That should have been instant. You should be able to take antiderivatives of single terms to exponents, right? So you need to see this as being maybe this is why I always sort of recommend that you write these uses like that, right? Because then these distributions are a lot more clear. So you're going to get what? U to the 3/2 minus u to the 1/2 du. So be careful. I'm definitely going to try to trick you with something like this on the midterm, where you're just going to have to distribute and it becomes easy. Okay, so what's the integral of this then? Well, let's do it piece by piece. What's the antiderivative of u to the 3/2?
Almost
2/5.
Yeah, same thing.
No, literally the opposite.
Divided by 5 over 2, which is the same.
Oh, you said divide over.
Yeah.
Okay, she is right. Sorry, I apologize. Mea culpa, mass mea culpa. So this is how I usually do it. I just take u and I add 1 to the exponent. In this case, you get 3 halves. And then I just make sure to divide by 2/3, which is equivalent to multiplying by 3 halves. You can check. If you take this down, those are going to cancel. If you take that down, those are going to cancel. I'm just going to throw in my constant. And there you go. That's the integral. I guess we should undo the... Pardon me?
Shouldn't it be 2 over 3? Because then when you multiply between the
Oh, yes. Sorry. 2 over 3. Thank you. Okay, then let's undo our substitution. So we know that u is 2x plus 1, so we're going to get 2/5. Well, I guess maybe I should distribute that quarter. No, who cares? 2/5, 2x plus 1 to the 5 halves, minus 2/3, 2x plus 1 to the 3 halves plus c. Okay, substitution. So you guys got to get really good at this, right? Do as many problems as you can. There's not much time, right? Every night you should be doing as many of these problems as you can, right? Because if you wait till the last minute to study for the next midterm, you will fail, for sure, right? I can't even give you easy integral questions if you haven't been studying. There's really no such thing as an easy integral question. All right, so take that over. Like, look at that, study. We're going to do another one while I wipe down the board. So the good news, if it is good news, is that I'm not developing much theory anymore. Like, these lectures are just going to be me practicing with you, doing as many problems as I can for you. Okay, so today we have to move from, what kind of integral was that up there? Do you have the name for it? Bob? Alice? Indefinite integral. Right, so remember that when we were developing area under the curve, we were always going over some finite interval. There's no interval up there. Right, we're not moving from a to b. We're just taking an integral. Right, so this basically is the new notation for antiderivative. Right, so we have antiderivatives and indefinite integrals are now equivalent. All right, so what we want to move from indefinite integrals to definite integrals. And in particular, definite integral substitution. So how do you do a definite integral? Well, remember, we have fundamental theorem of calculus part 2, which says the integral from a to b of f of x dx is equal to the difference, f of b minus f of a, when f is the antiderivative. We're going to extend this a little bit to be used with substitution. So the new theorem looks something like this. If we go from a to b of f of g of x, g prime of x, b of x, and we let u equal the g of x, then this guy is going to be equal to integral, and this is the tricky part. I'm going to put in the other thing first. It's going to be f of u du. This is the only thing you really have to remember. If you can do indefinite substitution, you can do definite substitution. The only tricky thing is you also have to perform substitution on these indexes. Right? The fact that this differential says dx is basically implicitly telling you that you're running a along x to b along x. Right? These new indices here now have to be with respect to u, not x. Right, so we're also going to have to perform substitution on the indexes. Okay. So we're going to do an example, and today I'm going to do, this is going to be weird, maybe not. I'm going to do an example, and I'm going to do it like 4 different ways. Right? Because there's not one way of doing something. There are multiple ways of doing something. And often it's the case if you choose one of those ways, it's better than if you do it one of the other ways. So here's an example. We're going to try to integrate from -1 to 1, 3x squared x cubed plus 1 to the half dx. And remember, since this is dx, you shouldn't really write this. I'm just going to write it in for this example only, right, to sort of emphasize the fact that these indices are running over x. Okay, so we're going to do the first method. And the first method, substitution method 1. Okay, this method we are going to adjust the boundaries. All right. So what substitution do you think we should perform here?
X cubed plus 1 equals u.
Yes, but I'll give you bonus points if you raise your hand first.
Oh,
Okay, so let's say u is equal x cubed plus 1. This means that du is 3x squared dx. What else do we need? Okay, so how does that adjust this? Sorry, the main event. So this is what I'm going to write. Maybe a little bit of a new notation, but I think it's a useful notation. Right? I'm going to say, well, if u is this, that means the derivative of u has to look like this. I'm going to say x goes from -1 to 1. And these two dots are an interval. I'm saying x is going from -1 to 1. So what does that imply about u? That means u is going from, well, how do I get now the interval over u? Do I have a relationship between x and u? Yeah.
plug it in.
Plug it in, right? So what happens if I put -1 into here?
U equals 0.
0. And then I go to what? 2. Okay, great. These are the old indexes. These are the new indexes? Indices. And these are the new indices. So this is going to be equal to 0 to 2. Let me see. So look, we got 3x squared dx. That's 3x squared dx is du. And then this becomes u half. Okay, finish this for me. What do I do? Finish it for me, and I'll come back. Anyone have an answer for me? Nope. All right, well, what's the antiderivative of u to the half? What did we just do, right? So we increase the exponent by 1 with 3/2, and then we make sure to cancel that out, and then we have to go from 0 to 2. This is going to be 2/3, 2 to the 3/2 minus 0 to the 3/2. 2 to the 3/2 is square root of 2 cubed, which is 2 root 2. Or, if you prefer, it's the square root of 8, which is 2 root 2. So this is 2 root 2. We're going to get 4 root 2/3. Anyone else get that?
So, can we go?
Hold on, I'm going to open this like we're in a movie theater. Yes.
Doesn't du become u? Don't you just find the antiderivative of that as well?
What?
What happens to du?
Du is the thing telling you what to integrate with respect to. It's gone. Well, why didn't you ask? This is the first time you've asked that.
Yeah, I
We've
know.
just substituted something else, right? What do you mean what happens to the du? This is just notation. It's saying integrate this with respect to u. That's what it's saying. Because if I integrated this with respect to x, u would be constant, and this would be totally different. Like, forbidden board. What's the integral of 1 with respect to x? Shh. Oh boy.
What was the question?
What's the integral of 1 with respect to x? Well, with x plus c. Okay. That's a constant, right? I can put any constant there. Yeah? So what's the integral of a with respect to x? Okay, if this thing is independent of what you're integrating with respect to, it's considered constant. Yeah, makes sense?
Yeah.
Okay, so that's why we have to indicate at the end of the integral what we are integrating with respect to. The same thing with derivatives, right? The dx underneath is saying I'm moving along the x-axis. Because remember, this is also notation for something geometric that we set up. We're measuring Riemann sums. And what were we doing? We're moving along one of the axes, setting up rectangles. This is telling you what axis to move along to set up the rectangles. There's going to be a bunch of options. Yeah? Okay.
And we don't write the plus c in this situation.
You have to write the plus c if it's an indeterminate one.
Yeah.
We don't do it in this case because they will cancel. Right? That's the other thing. Maybe I should mention that. Right? So if I put boundaries on here now, 0 to 1, and then I take this from 0 to 1, what you're going to get is 1 plus c minus 0 plus c. So like in all cases, those constants will cancel. All cases. So when we're doing definite integrals, we don't bother writing down the constant because it's just going to disappear. Yeah? Okay. I thought you guys would have talked about this last class. Yeah?
So in this case, you use both theorems?
What theorems?
Like the fundamental theorem?
No, I don't. I didn't use it at all. I just used substitution.
Isn't that what you did on the right, the first theorem?
Oh, yes. I guess technically, yes.
Okay.
Yeah. You don't have to state it or anything.
No, I'm just trying to like figure out to do like different questions based on that.
Well, like in order for me to claim that this is the area under the curve now, you needed last class to say, look, the antiderivatives are truly giving us the area under the curve. Right? That's that connection that was supposed to be made last class. Right? So now instead of going through this geometric Riemann sum and taking limits, we're just going to do an integral, right, and call it a day. Okay. So that was method 1. Let's do method 2. So method 2 goes like this. What we're going to do is just do the indefinite integral first, and then revert. Right? So we're going to do indefinite first, and then we're just going to undo it. Substitution mention 2. So we have the integral of 3x squared x cubed plus 1 to the half dx with u equal to x cubed plus 1, which means du is 3x squared dx. So that means I can write this as integral u half du, which then gives me 2/3 u to the 3/2 plus c. But now I can undo it. Right? Now I can put x back in. So I have u is equal to x cubed plus 1. So this is really 2/3 x cubed plus 1 to the 3/2 plus c, which itself implies that the integral from 0, was it 0? What was the original integral? Minus 1. Minus 1 to 1 of 2/3 x cubed plus 1 to the 3/2 dx now. Right, so I put back the bounds. Right, so now I'm using the old bounds because we've properly found the integral with respect to x. So this is going to be 2/3 x cubed plus 1 to the 3/2 from minus 1 to 1. And let's see what we get here. We're going to get 2/3. I hope I did this right. 2/3, 1 plus 1 is 2 to the 3/2 Minus what? Minus 1 cubed is minus 1. 0 to the 3/2. That's what I like to see. This is 2 root 2 times 2/3 is 4 root 2/3. Okay, same thing. So there's no way of telling which way is the better way. Right? It just if you try to do it by adjusting the bounds, it may not work. You may not have a nice relationship between x and your substituting variable. In which case, you'd have to do this indeterminate one. Yeah?
So you should be pretty confident with both methods.
Yeah.
Okay.
Well, they're barely different. The hardest part of both methods is actually performing the substitution and integration. The rest is just sort of details, important details. Right. Okay, let's try another one. Or maybe I'll write it on the board and you guys can start thinking about it. Oh yeah, I'll do that. I'll just write it on the board so you can think about it while I wipe down the rest of the boards. Okay. So give this one a try. Integral minus pi quarter to pi quarter tan theta d theta. Was a student who had a revelation about tan in this class? Some student in my office hour had a revelation about tan. And that revelation is required here.
So what was the relation? So it's going to plus half the thing.
We'll give it a try. I need to distract you while I wipe down these boards. I'll make one lap. Oh boy. You only have one identity for tan. It's the 1 over sine over cos, the basic one. Step 1, tan theta is sine theta over cos theta. Right? Huh?
Isn't it just 0? Yeah, it is. Oh no, it isn't. Okay. Let u equal.
You went the wrong way. Why? Use either an be sine or cos. Well, you have sine and cos. There's only two options. Sine or use. I wish I could try to bring that ahead of time.
Yeah.
Okay, no problem. How's it going? Barely, sir. My dad is on this. That. Given these tools, you're going to need to know how to use all of the solutions to solve problems. I cannot tell you ahead of time which tool is useful for what integral. So the best answer I can give you is you have to use intuition. You got to keep moving. Not even the best physicists in the world can tell you ahead of time what to use. Integration is typically impossible, which is why we have to, like, I taught you about rooms to usually use the best that we can do. No, I'm in the midst of writing. But you shouldn't over-rely on it. So you know how so me and Mike both write into the minutes, and then we sit down, and then we pick questions. So I give you all like the questions that it's not necessarily specific.
No, I read
Yeah. Why, like, yeah, okay. Where did the line yeah, right?
Oh, du would be, if it's sine, it would be the other host, theta, d theta.
No, I think.
No, so it would be d, it would be u over d. Or no, u over, or u du. I don't know, I want to write it up.
Yeah, you gotta plug in the value.
No, all of that can be replaced with u. When you have u. That's what's going to happen. Any progress? Yes. Where did you stop?
It's really
That works. But I'll show you that you did way more work than necessary. I'm trying to keep it too messy.
That's the same. U is cos.
So, here, we rewrote it, it's PT, and then
You can't just do arbitrary. You can't just do arbitrary negative switches. First of all, that's the theta. dt would be t tan theta. That's what you wrote. That's not. That's where you're sleeping.
is this like still?
Oh, I think it's.
No, you're replacing that too.
So it's a respect of D here now.
Yes. You have to write it. Like maybe you should write it like this. What you wrote before was fine, but like if you write it like this, maybe now it becomes clear what you should do.
I don't think that's it. It's over.
Okay, well, I'm gonna work through it on the board. That's okay. Let's do it for everyone. Yeah, no problem. Yeah. Because I'm running out of time, so yeah. Okay, let's do this. Let's do this. Which substitution was better? Which one did you use? And which substitution method did you use? The second one or the first one?
Second.
Why? Too afraid to use the first one? You know why? I knew you would choose the second one. This is a very deliberately chosen example, and I'll show you. This is an example where you should have used the first method. All right, watch. Okay. Okay, so this is going to be equal to pi quarter to pi quarter. Sine theta over cos theta, d theta. I'm going to do the following substitution. I'm going to say u is equal to, I think I picked cos theta. The other one would have been fine as well. This means that du is equal to minus sine theta d theta. So note that I can replace minus du with sine theta d theta. That's this, sine theta d theta. So this is minus integral sine theta d theta gets replaced by du. Then I'm left with 1 over u, right? Okay, but I'm going to adjust the bounds. So what were the bounds with respect to theta? Theta, we're going to go from minus pi quarter to pi quarter. What does that mean about u? Okay, so u is going to be what? So cos of minus pi quarter to cos of pi quarter. Can anyone tell me what these are? We've forgotten our trig already? We're still going to need it. Cos of pi quarter. Anyone?
Is it root? No.
It's root 2 over 2. Right? Because you should have learned a long time ago about this triangle. Please don't forget basic trig, because I'm going to have to use really sophisticated trig in a bit. Yeah. Okay, stop. Watch. Look at my bounds. Look at my bounds. What do you notice? They're the same. Okay, so I'm integrating over an infinitely small interval. What does it have to be?
0. That's literally what I said at the beginning.
Ta-da!
Isn't it 1 over root 2?
Yeah, root 2 over 2 is the same thing as 1 over root 2.
Rationalize me.
Oh.
Okay, look, so here's an example where doing the method 1 was way better than doing method 2. Right? If you ever come to a situation like this on your midterm, hint, hint, don't keep going. Stop. I'm trying to test you if you know all of the little tricks, right? Because these little tricks are the only thing that are going to allow us to take integrals of anything. Does this conform to what our geometric expectation of this problem is? Don't forget that we have to always associate this back to pictures. Yes, why? More than that, though. And those areas are the same. Right, so if I draw tan, so tan looks like this, right? Minus pi half to pi half. And we do something like this. Whoa, that was terrible. Oh my God, that was terrible. Oh. I'll try to go through the middle this time. I broke the only rule. First you draw the curve, then you draw the axis. Okay. So there's pi half, there's minus pi half. Pi quarter is going to be here. Minus pi quarter is going to be there. So what do you notice about those two areas? They're equal. Right? So that means you could have concluded 0 without doing any integration, period. Right? So we may also do this on the midterm. Right? Just give you something which is odd, and then ask you to integrate over it. Right? So what are the general statements that we can pull out now? Right, so let's try to generalize this. So here's a theorem. Over the interval, okay, a special interval, a through a, right? Minus a through a. That means we're centered at 0 and going equally out on both sides. If f is odd, what does this imply about the integral? Yes, that's this situation. Tan's an odd function. What happens if f is even? What does that mean about the integral? What? Well, you better learn, right? What area?
Under the curve.
From what?
Take the right.
Perfect, right? It's 2 times the integral from 0 to a of f of x d of x, okay? That's the language we use. Right, this should be sort of obvious if I'm going to reuse this space. Okay, so if we take like an even function, I guess the standard one is like a parabola, right? And we take this area to a and we go to minus a, you're going to get that area. These areas are going to be the same. So it turns out we can just integrate from 0 and double it. All right, you're going to have to be using a lot of these sort of geometric exploits when doing integrals to try to make things easier.
That's like only if it's perfectly symmetrical, right? Like if it's shifted.
If it's shifted, then you can shift your interval.
Oh, okay.
Right?
Okay.
I can make a more general statement, but you're allowed to you're allowed to transform equations. The area doesn't change if you shift everything, as long as you're shifting the boundaries. So this is good enough, right? Because if you're centered somewhere else, you can do a substitution to get you centered back to the origin where this will apply. I don't want to complicate this by centering it somewhere else. Well, we're going to lose the essence of what I'm trying to say. But that's a good question. No, this is generally applicable anywhere where there's a symmetry. So don't forget, right? When you're dealing with these integrals, right? Like one of the integrals I had on my exam was something like this. They gave us a bunch of complicated equations, and it ended up looking like this. Right? Those who tried to algebraically integrate that were screwed from the get-go. Those who realized that this list of equations were describing those 3 shapes, easy. Could not have been easier to compute the thing. It's one of my earliest memories from university. I remember the girl beside me weeping so loudly that I had to be asked to move. Yeah, calculus is hard sometimes. Well, I was distracted. I also had someone try to get me to help them cheat. I'm like, well, what's in it for me? I'm like, how am I supposed to help someone cheat on like a math test? Okay, take the integral using the substitution sign. Then take the derivative. Now substitute that back in. The answer is pi root 2. Okay, I'm going to give you just a final, what time is it? I don't think I can afford to give you a break today. You guys want a little break? Has to be a true break. Okay, we'll skip it. Great. So I'm not going to do this one. Why don't you give it a try? Here's a little exercise for you. Integral 0 to 1. 5r over 4 plus r squared dr. Give that a go. I'm just going to wipe down the boards and prep for the second half of the lecture. But please study as hard as you can until August. That is the only way we're going to get through this. This is a sprint now. I want you guys to get the outcome that you want and deserve. But if you wait till the last minute, you're going to be overwhelmed. That's your warning. Because I hate to say it, this is the simplest of all the techniques. The techniques I'm going to show you are going to get more and more complicated. Everyone have this down? Give it a try. The solutions are in the scanned lecture notes, but give it a try first and then look at the solution. Reading solutions doesn't count as studying, right? Because understanding a solution is a totally different skill set than producing the solution. Right, so don't fool yourself by studying solutions and say, I could get that. It's like, well, prove it then. Prove that you can get it by trying. Okay, so now all we have to do is talk about the area between curves. What do I mean by that? Well, what happens if I want to compute the following area? call this A. Let's call that B. Let's call this the axis. Y equals 0. What happens? How can I get this area? All right, let's call this curve F and this curve G.
You could do the integral twice separately.
How would that help?
So I could do the one for F and the one for G.
Okay, so that's a good starting point. Let's think. All right, so here's A, here's B. So this was F, more or less. So if I take the area under the curve here, let's label it. Let's label this as A. Let's label this as B. Let's label this as C. This area down here is going to be D, but it includes this area. Right? Both in there and in here. And the area under the curve for G will include B as well. Okay, so what is the integral of F then with these labels?
All equal A plus B plus C.
Nope. Remember that when I write stuff like this, it's assumed that the areas themselves I'm writing are positive. I'm assuming that all of these are positive, as written.
A plus C minus B.
All of them are positive. We assume when we're writing area, when I'm bounding area, I'm putting in positive terms. Yeah.
Do you subtract a positive area?
Well, solve this question for me, please. Oh, shoot. Those were bad labels. I'm going to say S to T. S to T. Why not? S to T. Okay, so what is the integral from S to T? Okay, so this one's F. I want this area. How do I get that area? A plus C minus B. I'm going to write it like this. Yeah, same thing as agree? If it doesn't make sense, it has to make sense. All right, so please tell me. All right, so this is the most basic property of the integral. Right, is that it's basically just giving you the area, right, where this is negatively signed area. How then do I get the integral of G from S to T? What's that?
A plus C minus B minus
No, G.
Minus D minus B.
the area.
Well, G is just going to be this area.
Oh, does D include? Okay, so when this being negative D.
Minus D. Okay. Using those labels, what's this area?
Minus D plus A plus C.
Well, let's label the pieces we need. I need this. This is C. I need this. This is A. I need to remove this, right? And then I also need this, D. So what is it? Well, it's A plus D plus C. Oh, sorry, that was a B. Minus B. Agree? Okay. How can I combine these integrals to get this?
You could switch the integral from T to S instead of
Simpler
S.
than that. How can I combine those integrals to get that sum? Yeah,
You already have A minus B plus C in that expression, right?
and that's very close. What else do we need?
And then you can just do the negative integral of D, or you can put the negative sign in front of the integral,
You subtract that integral?
or you just do that.
Well, that's what you're describing, right? What's this? The integral from S to T of F dx minus the integral of G dx from S to T, which you know that the integral has this property, yeah? Right, that you can sort of move the sum. So, but what is this going to give us? This is going to give us A plus B, A minus B plus C minus D. which is equal to A plus C plus D minus B. So look, if f and g are two curves, and f is the one on the top and g is the one on the bottom, the integral over that interval of their difference gives you the area bounded by the curves. Right? This area here is going to be given by the integral of f minus g dx. That's all you have to understand from today's lecture, right? You just got to isolate the top curve and the bottom curve and integrate over it. So we'll do some examples. Or maybe I should give you a definition first. The area bounded by f and g over this interval is given by the integral from a to b of f minus g dx with a provision provided, that's very important, that f of x is greater than g over x or equal to for x in the interval. Right, this is just a statement that says f has to be the one on the top. Example. Find the bounded area, and I'm going to write that instead of write bounded area, by these two curves. Where do we have to start? Exactly. We need to identify which one of these curves is the bigger one. Right? You may not be given this information. You may have to determine it. Okay, so for this one, I'm going to run to the computer and plot for this one. What happens if it's on a test? We won't give you things that you're going to need to plot on a test. We'll give you something that's more readily provable that one is bigger than the other. But you may have to argue using other calculus. Right, like this function starts higher than this one, it increases faster or something like that. But in any case, here's the, I'll give you the plots. So we are going from, oh, also notice that they haven't given us did they give us an interval?
Yeah, but it switches.
Hold on, I didn't finish this. Find the bounded area by that and that over 0 to 1. Sorry. That's missing from the notes, so just make sure to add it back. Okay, so this curve actually looks like this. It starts at 0, 2, and ends at 1, 2 over e plus 1. So that's, this one is 2 over e to the x. And the other one sort of looks like this. That point there is 1 e half. And this point here is 0 a half. Okay, so we want, so that one here is ex2. I want this area, and we're going to go from 0 to 1. What is the integral I need to do? Sometimes I'm just going to say on a midterm, set me up the integral. That's it. That's all I want. You don't have to take it. So you also have to be very good at like encoding the problems into integrals, not necessarily just performing them. Actually, the setting up is way more important to me than the actual performance, because most real scientists just go to a computer. So what integral gives me the area here? Okay, what extra information do you need me to give you then? Yeah?
You could take the integral of the top and then subtract the integral of the bottom.
Over what interval?
Over 0 to 1.
Yes.
I have a question.
Yeah.
So for for the first graph, though, y equals 2 over e to the x.
Yeah.
When I plug in 1, wouldn't it be 2 over e?
Oh, did I
You
do?
wrote 2 over e plus 1.
No, no, no. I think I missed. Sorry. You are correct. Thank you for pointing this out.
Okay.
Sorry.
You have to be small.
You're right. You're right. That makes me happy. You're paying attention, right? Okay, so you're saying I need to take the integral from 0 to 1 of what? Right, so, sorry. Of 2 e to the x plus x, that's the top curve, minus the bottom curve, e to the x half dx. Can you guys do that? Try it. I'll make one lap.
The derivative of e to the x. No, no, it equals e to the x times what's f of the exponent. But remember the derivative of x is just 1. So this is what it equals. It's just, yeah. But let's say e to the 2x, right? The derivative would be e to the 2x times 2 because you're bringing that down. Doesn't change. Anyways. Plus. You kind of just have to, you can just kind of work out this one. So I'm just going through it. And then from 0 to 1.
Oh, that's that.
Yeah. And then I'm working
Oh,
It's sentence.
Terminology I've never seen.
And then 1 over 2 e to the x.
Terminology and concepts that haven't ever been introduced.
The derivative of 1 over 2 e to the x would just be 1 over 2 e to the x. Cool.
Partition is just like we're breaking. That's like the rectangle.
Right. But it's negative.
Partition.
Yeah, because then, like, it gave like.
Break into parts. You can still like use English.
No, but if you could do this. This equals 0 to 1, 2 over e to the x dx minus the other one.
Oh, you want to
Minus.
Oh, yeah, just as always.
I mean, you could. No, we could, but we're doing the exact same thing. It's literally over the same exact interval. You subtract the same value.
We give you these
Doing the way you find is the best way.
just so you can figure out what's the sum before you do a midterm where it's going to be a serious function. That's the point of these quizzes. It's a signal before going into the midterms. I wouldn't stress that too much. So we made the least amount of marks possible.
Yeah, that's.
Well, if you choose to like not correct those misunderstandings. Well, like whenever you take an area over a curve, you're still gonna have to make some samples. Those samples form real. And there's question you read the textbook, which definitely talks about partition.
It was like different when we were actually like doing
One minus
I don't know, like there were things that I felt so everything else like you know they have like like they're different you know the next term.
I'm just going, and then you plug in the intervals. At least that's
You're not taking the direct because it's like our setting was like their average and like are always like equal.
Definitely that's what random
So
sample.
yeah, but like you could have said one question might say like let partition be and then like all these different like notations and curly brackets blah 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 and I'm like what does that mean? Because like when I'm thinking curly brackets I'm thinking this is the set of this function. It's like it was that so I'm like what partition I'm like what
If you're given a random sample, if you gave you a collection of points, that's a random sample.
yeah, so I saw it as a collection of points, but then that and I think
But the thing is, when they gave me that set, it was just 1, 2, 4, 7, not but then the term was 1, 2, 3, 4, 5, 6, 7.
Skip the sample.
Yeah, I didn't do that. Okay, I fixed that.
Here are your sample points.
So you're the editor.
like you know, the other professors teach you French, and you're given a test in French, and you're like, what the fuck? Like,
Did you do it?
Well, if there's some terminology problems.
like everybody left like this,
I
stayed, but like I would still
And then I just took the number and I used everything. You just kind of have to figure it out. I mean, like, I raised it back a little, so it's easier.
I kept doing that. I'm like,
And then this is what I can make sure my discretion
So it was.
So yeah, just, so yeah, 2e to the negative x is the answer. So I get back. I'm going to make it negative 2. If you take the derivative of this, you can just see that it works. Hopefully we can figure it out there. So look, this becomes negative 2 e to the negative x. But then take the chain down. The derivative of negative x. Why just becomes negative 2, right? And then this negative in front that I put there cancels out, and it becomes 2 negative x.
The interval part of that, if you draw a line,
So that one is the same 50. No, but like if it's just a constant, it's attached to something that has a variable. So
Right,
it's
so
no
that
longer
was constructive based on the fact that they gave me already an entire graph, but they gave
I
me
feel like just like doing these kind of intervals is really especially yeah, so it's dumb stuff.
function tells you everything.
Okay, I didn't
like someone introduced this whole time we were doing like
I thought it was specifically like that. It was everything under this entire non-useful scope. So it was either you were given this specific point and you had to construct it, or it was like give them
I'm like I did understand the question. I just did it for the graph.
Yeah, me too. It was wrong. Yeah, I did it based on the graph. So I took
You guys like don't consult with the
For one, I'm assuming you're reading the text.
On the interval from 0 to 1.
And I wanted to
There's no chain rule.
yeah, there was 2 of the same.
So you find the antiderivatives of each term. The antiderivative of 2 over e to the x and the antiderivative.
And then the partition is bigger, right?
Got it? You find that, and then you set it to the interval. Remember that line notation you did? From 0 to 1. 0 at the bottom.
So that number happens.
You're going to subtract when you sub in the top number, the same expression, minus the same expression with 0. And
So the quiz, did that go poorly?
we should have the index stuff.
Give me some feedback.
He got ours.
Yeah.
Partition kind of threw me off because I didn't know. At first, I did the collection of all the points 1 to 7, and then I realized it was exclusively on the partition, and like finding the area only at certain points.
Yeah.
Yeah.
That's okay, but we talked about random samples, yeah? Okay. Maybe I'll give you some extra random sample questions. So like the purpose of these quizzes is so we can catch these problems before the midterm is written, right? So this is a little signal for both you and us, so we can correct things before the midterm happens. So let's correct this misunderstanding before the midterm, where a mistake will be fatal, right? So I may give you some more random sample reading in some questions, right? But fundamentally, all we're doing is you're taking like an interval, and then you have to break it into pieces, which is called partitioning it. That's an English word that means to break into pieces. And then you just form rectangles wherever you've decided to make samples. So we mostly talked about forming equally spaced samples using left and right endpoints. But the random sample is the easiest. That's someone saying, here, evaluate at these points. Right? And then you just have to figure out how your rectangles fit.
Was that for that question? Is that to find the? It was like a random sample at selected points, and I think it's an and the partition. So were you supposed to add those random sampling points to the random point?
It's a random sample. Okay, I'll have to take a look more carefully. Maybe we can throw you. If you're just given a random sample of 3 points, you should have 2 rectangles, right? In between. Yeah. Oh, okay. So let's. Okay, so I'll rethink that. But anyways, we'll correct this before the big mistake is made on the midterm. Right? It's not a very expensive mistake. Okay. So what's the answer here? So what's the integral of this? Antiderivative?
-2 e to the negative x. Well,
Minus 2
-2
e over x plus x squared half minus e to the x half. That one's easy. We want to go from 0 to 1. Right, so you get minus 2 over e plus 1 over 2 minus e over 2 minus the bottom minus 2 over e to the 0 minus 0 over 2 minus e to the 0 over 2. This is going to be what? What does this simplify to? I'm holding the wrong piece of paper.
-2 minus 1 over 2.
Yeah, so you can, this one and this one cancels, I think.
Wait, what now? E to the 0 is 1.
What? Oh, sorry. Yeah. This just ends up being, I'm out of my group. Minus 2, this ends up being 3 minus 2 over e minus e half. There's no cancellation there. Okay. Let's try another question. I'm just going to delete this. Oh, sorry. I've already copied them for you. 3 over 2e minus e half. Okay, whatever. All right, find the area enclosed by y equals 2 minus x squared, y equals minus x, and note in this case, I'm not giving you an interval because these curves bound an area naturally. So let's just draw a picture. So this would be totally fine on a midterm. I expect you to be able to plot parabolas and lines. Is that fair? Okay. So here's the parabola, downward pointing. It has vertex at x equals 0. We should be at 0, 2. We're going to have a line. So I think this is root 2. This is minus root 2. I think I already blew it. I think I need to make this a lot longer. And then we have to cut this with a line like this. This is going to be y equals minus x. This curve here is going to be y equal 2 minus x squared. And you see that we've naturally bounded an area. How do I get that area? Maybe we can just set up the integral and call it a day. Well, not for the class, but for this example.
Is that how we do it?
Huh?
We just set up the integral and go.
Yeah, like sometimes I'll just say set up the integral and move on. I want to test different things. Can you take an integral? That's one thing I want to test. Can you use the integral to measure something? That's another test. And I don't want to combine two things at once.
So we're not expected to find where they intersect and then.
Of course you're expected to find where they intersect. How else are you supposed to do this?
Well, for this question, you said just set up the integral.
Set up the integral. You need the boundaries, right?
Okay. Well, I wasn't going to evaluate it. That's why.
Don't evaluate the integral, but you still have to set it up, which there's still a lot of work to go into setting up the integral. So set me up the integral that gives me that area. Yes. Okay, so step 1, tell me what these points are. Yeah, that's exactly correct, right? We have to make these two things equal to each other. So when these two things are equal to each other, what do we get? We get the equation. Okay, so if this is equal to this, I'm going to move everything that way. So you're going to get x squared minus x minus 2 is equal to 0. Now what? Factor. Okay, factor. What two numbers multiply to negative? What two numbers add to -1 and multiply to -2? Yeah. Is that correct? Minus 2x plus x minus 2. Okay. So what are the points of intersection? Yeah. So this is going to be 1, 1, and this one's going to be -2.
No, it's the other one.
Did I do it the wrong way?
Yeah.
Oh, yeah, it's, sorry. This means x is 2 and negative. Yeah, see, even I make these tiny mistakes. Okay, thank you. So this is going to be 2. Oh, I just used the line. Minus 2. Okay, and this is going to be minus 1, 1. All right, so that means we have to integrate from -1 to 2. So what's the integral? You got most of the pieces now, right? You got the integral. You just need to know what function's on top and what function's on bottom and take the integral of the difference.
Well, curve is always on top.
Yeah, this one's always on top. This one's always on the bottom.
Yeah.
All right, so I need to go, the bounded area is equal to the integral from -1 to 2 of the top curve. That's 2 minus x squared minus the bottom curve. That's minus x dx. And this will be very simple to evaluate. This is polynomial. I'll just tell you that it ends up being 9/2. Go home and finish this. You guys can tell me what you want on the test.
This. But this exact question.
That was so fast.
You want this on the test?
This exact question on the test.
You'll memorize it. So like what?
So change the points.
Yeah.
That is not the same. I will give you this to you
Give a
with
similar
one twist.
Okay.
I'm not telling you the twist.
Not a twist. This.
I'll give it to you.
Really?
Yeah.
Like that. Without a twist. Without a twist. No twist. He's gonna twist, flip it, and then add another curve.
No, it's gonna be like 3 curves for like 2 parabolas.
Could you do it along the other axis?
Well, why?
Yeah.
Probably.
Okay.
Oh, he's
Probably not figure it out. You just flip it so it makes sense.
Okay, try this one.
Yeah, I can visualize it. It's one thing to do.
It's literally the same area, except for using the y as your x.
Oh, he's gonna give us x.
Find the bounded area in the first quadrant. Bounded above. By y equals root x. And below by y equals x minus 2. Okay, first draw a picture for me. So in the notes, I've done this question 4 times. I've given you 4 different ways of doing this. Right, so first I want to make sure that you can actually produce the plot for this. It should be easy. It's a line and the square root function. So draw the picture, one left. And find the intersection points. It's the other thing you got to do.
Minus 2.
Yeah, you guys have made me feel guilty. I'll try to make it up. I will put that on the midterm.
Sorry?
I have questions.
Yeah.
Now it says we should be able to do it along the y-axis. Just like my transposite. Right? So everything would be the same. What I would do is flip the y and the x for the original equations.
You'd have to integrate along the y-axis. That means you have to express all the equations will have to be functions of y.
Okay.
You have to like express everything in terms of x, and then integrate along y. Which means you have to use the what you tell me what the integration boundaries are. For x, it was minus 1 to 2. What are we going to do along y?
We have to find what y values.
You can already read it. I've labeled it. What's the interval you'd have to integrate?
Oh, from -2 to 1.
No, that's where you stop. I think I have to go from -2 to +2. That's the range in y.
So it's not when you intersect the y.
Don't overcomplicate it. If you have the picture, you just have to walk along certain areas. Take slices. So this problem, you will be doing it in terms of y as well. Because it will be easier.
You said oh, you could say, okay, look.
What the heck?
So if you set it up as imagine let u equals square root of x. This becomes u squared minus n plus 2. It's literally the exact same. If you do the substitution, like let u equal square root of x. And then what would u equal? Or what would that equal? That would be u squared. Or
Does your picture look something like this? What's the area we want? It's this, correct? You didn't include this, right? Because this is the first quadrant. Okay. Good. Okay, so now I need to know what integral I'm doing. So where should I stop and where should I start?
Start at 0.
You sure?
I mean, yeah.
I start here? Would that include this area? Well, okay, tell me what you're integrating over then. Okay, let's pause, because we're definitely going to have to go from here to here. So what's this point? Where is the square root of x equal to x minus 2? You can guess. For what number is the square root of that number equal to x minus 2? Now let's just try the squares that we know. 1? No, 4? Square root of 4? 4 minus 2? Okay. Guessing is an option when doing these things. Okay, so we need to set up some integrals, right? So we'll call this guy f, the square root. Let's call this one g. So tell me the integral that you need to do. Even if it's wrong, we can correct it. Okay, well, let's start here. What happens if I take the integral from 0 to 4 of f minus g? Is this correct?
That'll give you the area under it as well, right?
Okay, so that will also give this.
Can't you just subtract it?
Okay, stop. Brilliant. Okay? Technique 1. Realize that this is going to give you everything, and just remove the area of that triangle, which you can calculate with the area of a triangle. That's one way you can do this. Okay, but what's another way you can do it? And that's in the notes, right? Can you give me an integral which will work?
Can you do like the area under square root of x and then subtract the next?
Yes,
Okay.
exactly. Break it into two pieces. This piece here, this is the integral from 0 to 1 underneath f. Right? That won't include this. This is what the definition of the integral is. The area under that curve. And then for here, we can use the difference one, right? The bounded area one. So an integral for the bounded area here could be given by this. The integral from 0 to 1 of root x dx minus the integral of 1 to 4 of the difference of the top minus bottom. Top minus bottom. You can work that out at home. One more way. Give me one more way of solving this problem.
With the first integral, the one you wrote there, 0 to 1 of the square root of x, would that just give you the area between the x-axis and
This, it gives me this.
this? Right?
Yeah.
So why are we adding them?
Because I want this area plus this area to get the whole area.
Yes, so isn't that...
Oh, yeah, sorry. Yeah. My apologies. Yes, miss.
How did you get 1?
Here?
Yeah.
Isn't that where this intersects, the axis? Did I do it wrong?
2.
Oh, 2. Sorry, guys. Remember, I do that on purpose to make sure you're paying attention.
Yeah.
All my mistakes are deliberate.
Carry fell.
One more way of doing this.
Could you do like all the area under root x?
Huh?
Like, what if you, from 0 to 4, all of the area under, root x?
And then just remove the triangle.
Can you do that?
Yeah, but that's basically equivalent to the first thing that you said.
Okay.
With like utilizing the picture and removing areas of stuff is a good technique. But that really, you only get that option when you start generating triangles.
Okay.
So if you have a line, then you should be like, maybe there's some geometry I can exploit here. But there is one more way of doing this. You got to think sort of more differently. So remember, we're integrating by creating rectangles along the x-axis. Nothing's preventing us from integrating along the y-axis and generating rectangles this direction. Yeah? Like, I know that seems uncomfortable, but like we can just decide to make our rectangles like here. And if I integrate along this way, then it's easy. You always have this top curve minus this bottom curve. Right? So along y, the bounded area becomes integral. Now I have to do this along y. Y. So we go from y equals 0 to, what is this point here? I think this was 2. 4, 2. Okay? So we need to integrate along y from 0 to 4. Along y. I'm losing it today. 2. And the top curve is this one, and the bottom curve is this one, if we're orienting our way along here. Right? So you've got to sort of like rotate this graph. So the top one is going to be this guy, but I have to express it in terms of y. So really this was y equals x minus 2, which means x is equal to y plus 2. This is y is equal to x, which means that x is equal to y squared. So this is y squared, the bottom one. This is y plus 2, the top one. So you get y plus 2 minus y squared. Single integral will give you that area. So I gave you 4 ways of doing this problem. You should go home and work it out and make sure you get the same answer each time. Okay? Any questions? You have to practice a lot now. You got to go home and like practice this. Because tomorrow I'm going to be giving you way more complicated stuff. And then next week, even more complicated. Right? So I'm begging you to try to keep up, or you'll get really overwhelmed. Right? This stuff is hard to learn at the regular pace, let alone the double pace that we're working at. Okay, so I'm going to give you some exercises. There's also a worksheet today. But otherwise, the lecture is over. Okay. Have a good one. Oh, all of this should work out to 10/3. If you do it properly. And if I did it properly. You too. guys. No, I wrote, it's not right. All right, I have to forget this one now. Maybe I can just invent something. All right, forget about it. I'll correct it.
Wait, are we expected to do
Pardon me?
It's enclosed by 3 curves. Are we expected to do?
Yeah.
That's what she's saying.
Every time I teach you something
Three
that,
class? Or is there 4? Like, does it keep
every
going?
time I teach you something for 2 things, that immediately extends to n many things. Right? A rule for 2 is a rule for all, right? Because you have a group of stuff, you remove one out, and then you have 2 things, and you can recursively do that. Right? So had I given you the right, I don't know the formulas because I wrote it down wrong, but like what I was expecting was like for this problem to be broken up, right? Into regions where you can individually take these areas. It's not going to be easy. We're going to have to think. There's like no such thing as a routine integral question. I feel bad. Like this stuff is hard. I wish I had you like twice as long during the week. I wish we had 3 months to do this, but we don't. I'm just trying to do the best I can for you guys. You got to practice. Anyways, don't do this one because I obviously wrote down the wrong equation. I'll put it on Piazza or something. But with practice, you can do it, I'm sure.